Welcome. Do you know what time it is? It's time for another patch from scratch. This is my last patch in this July Let's Explore series. And so I was thinking maybe we close things out with a fun Benjolin patch. My plan for today is to take the modules that I have here and put together a Benjolin and a rungler and talk through that patching process as a starting point for where today's patch goes. I love the Benjolin and the rungler as concepts because they have to do with structures of chaos, not just randomness or plain noise of unpredictability, but a unpredictability and complexity that has some structure to it. And in structure comes character. And so I think that the Benjolin and the rungler are such great concepts and sort of design patterns for working with structured chaos, characterful chaos, which is why I always keep coming back to them. If you're not familiar with these ideas about the rungler, the Benjolin, the work generally of the synth designer Rob Hordyke, you should go on a wiki rabbit hole. You should go look at these things because I think you will find a lot of interesting ideas there and a lot of really fun sounds. So just take a quick YouTube surf. Check out Rob Hordyke, the Benjolin. And maybe if you're not familiar, I am very happy to introduce you to these ideas. If you are familiar, we're going to have a fun time. So let's start with the patch. My plan today is to make a Benjolin. A Benjolin has four sort of components to it. It has an oscillator, another oscillator. These two oscillators combine in the rungler, which is the sort of core chaos structure of the Benjolin. And then the output of these oscillators modified by the rungler structure goes to a filter. And that's going to be our Benjolin. So for starters, I'm going to use the interstellar radio and the Nibbler to get my two oscillators from the interstellar radio and the rungler, which I'll talk about more as sort of how that works from the Nibbler here. The basic way this patch works, by convention, I'm going to call the top, the carrier here, oscillator 1, and the second oscillator on the interstellar radio, oscillator 2. For now, we can think of these both as just two square wave oscillators. By convention, I'm going to use the bottom one, my oscillator 2, as the clock, the thing that is moving bits through the shift register on the rungler. And I'm going to save this because we're going to come back to that. I'm going to take my top output, my top oscillator, and run that into the shift data. Now you'll see some dots moving along here on the Nibbler. We're using the Nibbler as a shift register, which means that we have these four buckets that have data in them, either on or off. And every time that we get a clock pulse to shift, we take what's in the 1 bit, we move it to the 2 bit, we take what's in the 2 bit, we move it to the 4 bit, take what's in the 4, move it to the 8, take what's in the 8, throw it away. And so we sort of have this line of on and off that we carry down every time that we hit a shift pulse. To determine what goes into those on or off slots, we use the shift data. When shift data is high and we get a clock pulse, we put an on into that. When shift data is low and we get a clock pulse, we put a 0, nothing into that spot. And so that's our sort of core basic oscillators into the shift register. Where this starts to get interesting is when we introduce a little bit of feedback into the shift register. Instead of carrying those values down the data line and then just discarding them at the end, we can take that last output and loop it back around to the input. This is a linear feedback shift register. And so I'm going to take output 8 here and put it into the data XOR input on the Nibbler. The idea here is we now have two inputs going to the input of the shift register. You can see how the lights have changed as soon as I plug the out 8 in here. So we have our data stream that I was talking about before, high or low, and we also have the output of that final bit, the final bucket on the shift register, going back to the beginning. And so we take these two, and it's called the data XOR input because we do an exclusive OR logic operation between them. If one of them is high, then we put a high in. If neither of them is high, or if both of them are high, we put a 0 into that spot. So we sort of multiply these data streams together to create a more complex data stream running through the Nibbler and then back around to create that linear feedback for the shift register. And so now what do we do with this linear feedback shift register that we have? We get a stepped voltage from it. Instead of just working with those bits directly, we add those bits up in order to create a stepped voltage value. And that's going to be the control voltage of our rungler, our shift register output. So I'm going to run that back to the CV control on both sides of the interstellar radio. And we can listen to the output of the interstellar radio here. Let's hear what this sounds like. If you listen, you can hear that there are sort of two things going on in the sound stream. We have a constant tone, and then it's being sort of modulated or interrupted by a lower speed tone. In this case, our data is at audio rate, and our shift is at sub-audio rate. That's our clock pulse that we're running into the shift register here. This is our data up in the audio range. Of course, we can put both of these up in the audio range. Or we can move both of these down into the sub-audio range. And we're going to play with all of these. The lovely thing about the Benjolin is that it does something interesting at all of these points. But for now, we've taken this stepped output of our shift register, and we've run it back to the frequency control on both of our oscillators. The signal in for the interstellar radio is normal to the CV control for both of the oscillators, so it's really easy for me to take the stepped output and run it to both oscillators at the same time. So when I turn up the CV control here, we can start to get a unpredictable, chaotic melody out of our system. And if I turn up the CV control to the clock as well, we'll start to get steps of uneven length. Our higher pitch steps will be shorter, and our lower pitch steps will be longer. And so we're getting towards our rungler setup here. There's one more really important idea that I think often gets skipped over in this discussion of the rungler that I want to add here to this. And that is with the classic rungler and with the Benjolin, you can lock this pattern. It instead of just being an endless stream of chaos as we get the difference between our output of the shift register and our new data input, we can lock it into a loop. And so we get the same thing over and over again. How do we do that with this setup that we have here? Well, what we can do is we can bias our input to be, we can sort of shrink. Right now, the input is either on or off. And we can shift that input so that it's more likely always on or more likely always off. And then that creates a constant number that the final output of the shift register is comparing against, which creates our cycles. I think that will make more sense when I show it. So what I'm going to do here, I'm going to take that data output and I'm going to run it, just for my convenience here, into a 2-channel mixer. And it's going to go into channel 1 here, just a standard positive signal, the same thing that we were listening to. But next to it, I'm going to put an offset. So now we have our signal and we can push it either to always positive or push it to always negative or always 0. So let's hear what this sounds like. So here in the middle, we have our chaotic stream, but as I bias the signal one way or the other, now we get a 4-step repeating pattern because the data input is always 0 now. We've put an offset on it so it never quite gets high enough to trigger a positive value at the shift input. So we're only getting out 8 plus 0. Out 8 combined with 0 is always going to be out 8. And so that creates a solid loop. Now what's really interesting is what happens when we bias our data in the other direction. If you listen, we have a locked pattern again, but it's twice the length of the pattern that we had before. What's happening now is that we have an always positive value. And so the result of that, this requires a little bit of thinking, a little bit of logic, but when our input is always positive and it's combining with the output of the shift register, what happens is we get an inversion of the shift register. If we always have a 1 at the data and we have a 1 at the input, that 1 becomes a 0. And if we have a 0 at the input compared against the 1 that's always at the data, that 0 becomes a 1. And so we still get a loop because of the constant value here, but it loops through and then it inverts itself and it loops through again and inverts itself back and forth. And so we end up with a sequence of twice the length where it goes through on one side and then that same sequence inverted. So now we can have locking patterns with the Nibbler. I should note that the Nibbler is a slightly different shift register than what you see in the Benjolin and a classic rungler. This is a 4-bit shift register. It has 4 of these buckets that I've been talking about, whereas an 8-bit shift register is going to have 8 buckets in sequence. And the way that the stepped voltage is constructed, on the Nibbler, it uses all 4 of our buckets, our bits, in order to construct this stepped voltage. But on the rungler, it generally only takes the last 3 bits and uses those to construct the stepped voltage. So there are some differences in the exact implementation of our shift register, but we can get a shift register that works exactly like a rungler here. We can get those uneven step sizes again. And this means that we're most of the way now with this locking here. we are most of the way to a full Benjolin. We've got our 2 oscillators, we've got our rungler, we've got feedback from the rungler to the voltage control of our oscillators. And so now we just need to put a filter on this. So I'm going to take that combined output of the interstellar radio here, and I'm going to run that down to the multi-filter, which I will be using as my lovely filter for my Benjolin here. We can take any of the outputs. I'm going to take the variable output so that we can easily move between the different outputs. And the final connection that we need to make is we need to take a copy of our stepped input and run it to the frequency input of the multi-filter. The Nibbler, very conveniently, has 2 stepped outputs that are the same. One of them can be shifted, offset from the other, but we're not going to think about that right now. So these 2 outputs are functionally the same. One of them is going to our 2 oscillators. The other one is going to our filter frequency. And that's a Benjolin. This is our structure that we're working with here. These are our tools that we're working with. Of course, because of the way that we've patched this out, because of the way that I've patched this out of the modules that I have here, we have lots of additional hooks to come in and modify this system. But before we get to that, I just want to spend a moment more with this setup as it is and talk about the way that I think the rungler is most important, which is not as a stepped value in the sub-audio frequency, but as a source of noise at the audio frequency. As I turn up the clock, it gets faster and faster. Until it becomes a tone. Right now, I have the CV control turned all the way down. So we hear a standard periodicity. We hear a steady frequency. Well, right now we hear 2 steady frequencies because of both oscillators. But what I talked about before of the clock having those uneven step sizes, where some notes, the higher notes, were more compressed in time, and the lower notes were of longer duration in time. What this means is that we have a periodicity. We have a lack of a steady metric pulse. At the audio rate, once that rhythm becomes frequency, that becomes noise. Let me unlock it. But the really exciting thing here is that it isn't full spectrum white noise. What we have is a variety of different differences of frequency that we unpredictably alternate between. And we can control the depth of variation there. With a small CV adjustment, we get small perturbations, variations in the frequency. As we turn up the CV, we have bigger steps and smaller steps. And so we can control the sort of color or character of the noise by thinking about it in terms of these uneven frequencies and the difference of frequency between our short steps and our long steps. Now, when I lock the rungler, we get a steady tone again. And that's because even with the CV frequency up, we now have a fixed pattern of short and long, which means that we have a repeating waveform that's either 4 cycles or 8 cycles of the rungler long. And there's a lot of additional great tones that we can get with that. And so that's our Benjolin here. Back down in the sub-audio frequencies, of course. I'm going to turn up the resonance on the filter. Unlock it. It becomes lovely to ping as well into a resonant filter to take these sub-audio pulses of varying lengths and to attack the filter with all these little pings. And that's our rungler. That's our Benjolin, sorry. The rungler, the oscillators, the filter. That's what you get in a Benjolin. That's the sort of the basic thing here. I think it's taken me quite a bit of time in order to explain this. And I'm glad that I went into the detail that I did on the Nibbler. So thinking about how to expand upon this, with any of these hooks, we can add additional modules into the loop. We can add additional layers of feedback or disruption. I think that there are, let's see, what could we do really quickly to add some additional interest? With the Nibbler, we have these individual gate outs and gate ins. And so I think I'd like to just very briefly make the rungler a little, let's see what happens if we take one of our outputs, run it into a logic here, and do something with it. Let's do our own additional XOR with, we're just going to try a sample and hold on output of the filter here. Let's do low frequency, and let's sample it using our clock. And now we can take this and run this modified bit that we have back into gate 4. And now we can get a sort of a glitchy rungler, where we have this flow of bits that we were talking about, but bit 4 is going out, getting corrupted, and then coming back into the system. And so, compared to we can add additional layers of complexity or crunchiness into the rungler system that we have here. And you can start to hear some more of the noise character of the rungler there. So yeah, this has been a time flies. This went by for me much faster than I was expecting. I hope this has been clear. I hope you've seen something interesting in the Benjolin and the rungler and the way that they can be constructed. I think that this freeze to sort of like lock the loop of the Nibbler is really important and it's often overlooked. And I hope you've had a fun time. Thank you so much for everyone who has been following along. And maybe I'll do some more of these in the future. We'll see. It'll be fun, no matter what we do, because the goal is to explore and to have fun. And I hope that you, in your own modular explorations, explore and have fun. Thank you.